So, good morning, everyone. Welcome to the class for Intelligent User Interfaces. For this week, the lecture is going to be recorded and it will be available from the VLE site. Okay, so let's start with today's topic. Today's topic is all about agents and intelligent agents, what sort of models we're going to see, what are the benefits of having such adaptivity to the user as available to be shown by agents, the challenges that are associated to this and how to collect data from users are basically the main topics that we're going to be discussing in today's lecture. Okay, so let's start immediately with agents and intelligent agents. Now, when we think of complex systems, that is, systems consisting of several interdependent and interacting entities that determine the system behavior, there need to be new and more effective solutions to be able to address issues ranging from the definition of appropriate modeling formalisms and to the use of advanced system analysis methods. Now, there are sort of like two main categories for such systems. One's the artificial system that are built by humans, okay, and we've got different components belonging to various application domains, and these were originally conceived for working in isolation for a specific purpose and integrated in a common environment in order to achieve, one or more complex goals. Then there are the natural systems that are already existing in nature without the intervention of humans. We discussed these in terms of a complex network of biological entities belonging to different biological subsystems. Okay, for example, the nervous system, the circulatory system, the respiratory system, working together in a synergistic manner. Now, it is clear that for such classes of systems, agents would provide a suitable research approach thanks to their key features of autonomy and cooperation. A key role in the adoption of intelligent agents would be played by the environment, which represents the problem space in which the agents operate and in which the agents represent one possible resolution path. Now, it is important to note that the environment can be partially or fully observable. Observability would let the agent retrieve the information and perform computation on it in order to take decisions and consequent actions on the basis of the perceived information. Moreover, the environment itself can be deterministic or stochastic. As a consequence, if the environment is deterministic, its properties are well known and none of them are random, which means that the output of the model is fully determined by the values of its parameters and initial conditions. If the environment is stochastic, then some randomness and uncertainty will be present. In AI, an intelligent agent is an autonomous entity that observes through sensors and acts upon an environment using actuators. That is, it is an agent and directs its activity towards achieving goals. That is, it is rational, as defined in economics. Now, intelligent agents may also learn or use knowledge to achieve their goals. They may be very simple or very complex. A reflex machine, such as a thermostat, is an intelligent agent, but it's quite simple. Now, intelligent agents continuously perform three functions: perception of dynamic conditions in the environment, action to affect conditions in the environment, and reasoning to interpret perceptions, solve problems, draw inferences, and determine actions. So perception, action, and reasoning. From a more technical perspective, an intelligent agent is an entity in a program or environment capable of generating actions. So the fact that there's an agent, you are presupposing an action. Now, to summarize, some important characteristics of agents include the following: rationality. An agent is supposed to act in order to achieve its goals and does not act in such a way as to prevent its goals being achieved, at least insofar as its beliefs permit. Now, a rational agent is one that can take the right decision in every situation on the basis of a set of criteria used to measure the level of performance in terms of the success of the agent's behavior. Such performance measures should be based on the desired effect of the agent on the environment. In particular, the agent's rational behavior depends on the following. The first is the performance measure that defines success. The second one is the agent's knowledge of the environment. The third one is the actions that it is capable of performing. The fourth is the current sequence of perception. Now, in general, for every possible perception sequence, the agent is expected to take an action that will maximize its performance measure. Now, autonomy is the second important characteristic. An agent is able to take initiative and exercise a non-trivial degree of control over its own actions. Indeed, autonomy is the capacity to compensate for partial or incorrect prior knowledge, and it is usually achieved by learning. This is because an agent is not omniscient, and in practice, it does not know all. We know that. The actual or possible actions of its outcome of its actions. So it's not an all-knowing agent. Okay, but as a consequence, an exploration approach is necessary through which an agent performs an action to gather information, therefore increase its perception, and therefore change its behavior and perform the action. Now, there are a number of agent models that one can adopt and use according to the requirements. There is a simple reflex. Now, the decision of the action taken by the agent is only based on the current perception. The history and the perceptions gathered in the past are neglected. This model is based on condition-action rules, and it works if the environment is fully observable. There's a model-based reflex where the agent model works when the world is not fully observable. As a consequence, it is important that the agent would remember previous observations about the parts of the environment which it cannot observe in a particular period of time. And this would require supporting a model for representing the environment. There's also a goal-based agent. Now, this agent model aims at driving the agent to achieve a specific purpose, and the action to be taken depends on the current state and on what it is trying to accomplish. Sometimes achieving the goal requires a single action. In other cases, the goal to be reached is complex and therefore decomposed into multiple sub-goals, each of which would require one or more as a set of actions. In this case, the achievement of all sub-goals subsumes the achievement of the main goal. Usually, in this case, strategies, planning, and sifting through a search space for possible solution would be necessary. Then there are the utility-based agents, and this can be seen as a supporting or a complementary model to the goal-based model previously described. In this case, the agent knows the utility function, which is continuously monitored and exploited to estimate the distance between the goal and the current state of the agent. And then there's a learning agent, where the agent model has the capability of enriching its knowledge and abilities by observing and acting accordingly. This means that the agent is able to learn from past experiences in the environment, to predict the future, and in some cases, proactively affect the environment. Now, when discussing agents, we cannot overlook the fact that a surrounding environment is present. For instance, to provide percepts and the context in which the actions are attempted. Now, the environment can be considered as a first-class abstraction that provides the surrounding conditions for agents to exist, and it would mediate both the interaction among the agents and the access to resources. Now, there are several dimensions for the characterization of an environment, and in particular, the most relevant would be observability, Agents can have complete or partial access to the state of the environment. We mentioned this before. Determinism. In a deterministic environment, agents' actions have a single guaranteed effect. Dynamism. So in a static environment, agents can assume that no change happens during their own deliberation. And discreteness. Discreteness can refer to different aspects of the environment, namely its state, the way time is represented and managed, the perceptions and actions of the agents. And generally, in a discrete environment, there are a fixed, finite number of actions and perceptions. Now, clearly, the features of the environment heavily influence the design decisions about the agent architecture. And it must also be clarified that it is sometimes possible to take a simplified but still acceptable perspective on certain aspects of the environment in order to actually come up with applicable and tractable solutions. For example, within the gaming context, in a real-time strategic game, the modeler could superimpose a discrete representation of the continuous environment to support the coordination of units patrolling the area. An additional dimension of the agent environment space specifies whether the environment includes other agents, in this case also cooperative or the competitive attitude of agents, and therefore this will be a multi-agent characteristic. Now, another way of describing the agent environment space is that of considering it from the perspective of a design abstraction, supporting the activities of the designer or the engineer. There are 3 different levels of support that can be provided by the environment. There's the basic level, essentially just enabling the agents to directly access the deployment context. The abstraction level, filling in the conceptual gap between the agent abstraction and the low-level details of the deployment context, for example, wrapping a physical resource and providing access at agent's level of abstraction. And the interaction and mediation level that would support both forms of regulation to the mentioned resources, as well as mediating interactions among agents to support form of coordination. Now, the environment has a fundamental role in structuring the system, as we mentioned before. This is particularly relevant for applications such as the simulation of biological entities, in which the defined model, for example, represents a physical spatial structure. For example, let's say we're trying to model the human body or some portions of the tissues of a human body. But it can also be relevant in situations in which the model must consider other conceptual structures, such as organizational or societal ones. Whenever the computational model needs to represent a physical environment and to explicitly consider its spatial aspects and dynamics, even without involving the modeled agents, there is a need for a precise and systematic model of perception and action that is even more apparent than in other situations. So bottom line is, we need to really get as much meaningful information from the environment as we can, so that the agents can take the right decisions based on the right context at the right time. The notion of action, directly contributes to the definition of the agent. We've already said, if you think about agent, you're immediately thinking about what sort of actions the agent is going to take. Literally, agent can be viewed as the one who acts. Now, understanding the reciprocal dependencies between the individual agents and their surrounding environment, either physical or computational, therein including the space-time fabric, amounts to understanding which kind of actions produce which kind of effects, either intended or not, and on whom, either another agent or the portion of the environment. This is where the design comes in very, very importantly. Regardless of the purpose and the effects of the actions, it is apparent that actions are influenced by the subject. And we need to know, who is it? Is it another agent? Is it the environment? Is it the human? as well as by their surroundings. Where and when is the action taking place? Which properties would influence the action's outcome and feasibility? Now, when it comes to properties that might influence the action's outcome, we can think of the following, these three. So there's situatedness, being situated, that is the immersion within an environment, that is the property of being potentially influenced and in turn potentially capable of affecting someone or something. Actions are then situated by definition, regardless of whether they are practical or epistemic. They have a target, they have a source, they happen at a given time, possibly might have a duration and or a delay. They can affect a given space, either virtual or physical, and can cause some change, either intended or not. Thus, agents too are situated through actions. They can be regarded as being active at a given time, in a precise space, for a given observer, either because through actions they affect someone or something, or because their course of action has been influenced by someone or something. It is worth noting that situatedness directly relates to the notions of perception and practical reasoning. Perception is the tool by which agents and the environment become aware of their surroundings, right? And thus are potentially influenced by the activities therein. Practical reasoning is the tool by which the agents can deliberate about how to affect something or someone. Interactions then are situated too, following the same reasoning. Each of the participants in the interaction is situated. Then the interactions they carry out reciprocally, affecting each other, are situated too, both because they are actions, although communicative, and because the acting participants are situated in a context. Besides, the interactions may also be situated because they are mediated by some means external to the participants, example, the environment. In this case, since the environment is situated due to its very nature, any interaction it enables and constrains may be regarded as situated as well, through the properties of the environment, the flow of the time, the topology of the space, the existence of resources, and properties with their own dynamics. The second property, whether or not interactions are mediated by the environment, they always represent a social relationship between the parties involved. The complex and distributed dependencies within the agents, mostly regarding goals, delegation, and trust, are fundamental to the definition of intelligence as a social construct. In particular, the notion of social action, which is meant to reconcile the individual cognitive processes and social coordination, and provides a conceptual foundation on all social issues such as cooperation, collaboration, competition. Now, simulation is another property that represents an application context in which the notion of autonomous agents have become almost ubiquitous. The spotlight is on the resulting or emergent behavior of the local actions and interactions of relatively simple agents. Agent-based simulation refers to a model in which the dynamic processes of agent interaction are simulated repeatedly over time. Now, why use interface agents? Agents acting over the interface are meant mostly as a communicating tool with the end user, with a human. We have to note that most of the research work is often dedicated to making the agent more human-like, for example, through its responses, through its actions. What an interesting paper has come up with, it's in the VLE, is that sometimes this has the reverse effect on the users. When the interface agent is made to look more like a human, users expect to be dealing with a human and thus may be disappointed when the agent fails to act as so. We need to keep in mind that, as with the role of other agents, interface agents need to fulfill a goal within the context of the environment they are acting in. Okay, so there are pros and cons. So if, a person, let's talk about customer care, okay? And we have an agent that's representing customer care on the other side. If the agent is made to look and sound more like a human, then the moment it fails, there are going to be failures, because as much as we want, we're still far from reaching a human level of communication. Okay, we might have a decent level of communication where the person might have his or her his questions answered, but we're still far off from having a conversation that's really human-like, that can be broad. Having said that, when it's a closed theme and topic, then we're nearly there. So there might be some leading points where the human might not necessarily recognize that he's talking to an agent or she's talking to an agent. So there can be some sort of disappointment when the agent is revealed. However, we still have the potential when designing interface agents to enhance the usability of the actual application, and to exploit this human computer interaction area for all users. Now, interactions between an intelligent software agent and a human user are ubiquitous in everyday situations, such as access to information, entertainment, and purchases. Sometimes people don't even realize, and that's the beauty of it. They don't even realize that they're not dealing with an agent. Sometimes we picture agents as just the bots for customer care, but really and truly, when we go through these sites here, for example, Amazon, we are dealing with agents, and they have access to information, to entertainment, to purchases, and the ISA would mediate the user's access to the content and control some other aspect of the user experience. And this is not designed to be neutral about the outcomes of user choices. Okay, so the user here is sort of adapting its behavior in some non-trivial way to make the user experience better, of a better quality. Now, this recommender system, the Amazon one, okay, is a type of interface that mediates the interactions of an intelligent software agent and a human user, and is largely, if not entirely, under the control of the ISA. In these interactions, we assume that the user has a particular need. One needs to purchase something. And the ISA responsible for selecting the recommendations has the goal of increasing some form of engagement. Now, whether it's buying, whether it's clicking, whether it's sharing, whether it's liking, okay, so there's some form of engagement. The user's engagement is interpreted as signaling the relevance of the recommendations and is therefore considered as rewarding. Okay, now there are various measures of rewards, such as the click-through rate, the purchase. In the example shown, okay, before for Amazon, the ISA can recommend a selection of the relevant items along with supporting meta information, some images, descriptions, ranks, etc., which are designed to help the user make a decision. The user also retains the choice to leave at any given time, which would not normally be in the interest of the intelligent software agent. Now, the popularity of RSs is largely due to their availability both to increase the utility of boundedly rational users who would otherwise be unable to examine each item in the catalogue on their own, but also maximize the ISA's utility. Importantly, one can describe the goal of the ISA as maximizing the relevance for the user. Now, there are examples of systems where we can say that intelligence lies mostly in the interface. For example, systems with adaptive user interfaces that are automatically adapted to the inferred capabilities or needs of the user. multimodal systems that aim to enable more natural human-like forms of input and output. Systems with human-like virtual characters that enable the user to interact with a system in a way that is partly similar to human interaction. And then we've got smart environments in which embedded objects interact intelligently with their users, and personalized websites in which the displayed content is adapted to the inferred interests or needs of the user. Then there are other examples where the intelligence would lie behind the interface. So, for example, recommender systems that present products, documents, and other, so the intelligence is behind that. The systems that employ intelligent technology to support information retrieval, learning environments that often offer learning assistance on the basis of assessments. Interface agents that perform complex or repetitive tasks with some guidance from the user. Situated assistance systems that monitor and support a user's daily activities. Systems for capturing knowledge from domain experts. Games that make use of AI technology to create opponents against which the human players play. So you can see there's the interface, but the intelligence is lying behind the actual interface. Whereas here, these are systems where the intelligence is in the UI. Okay, so there are various ways in which user models might be applied for a user adaptive system in order to make predictions or decisions about the user. This is, for example, something that is adopted from Amazon. If we go back to our previous example of Amazon, we can see how so the user adaptive system can be defined on the following: an interactive system that adapts its behavior to individual users on the basis of processes of user model acquisition and application that involves some form of learning, some form of inference, or decision making. So when we take into consideration user adaptivity as one of the characteristics of an intelligent interface, then we have to think of a system that would adapt its behavior, an agent system that adapts its behavior to the individual users on the basis of processes of user model acquisition. Before we spoke about the environment and the importance of acquiring information from the environment through perception. But when we talk about an interactive agent system that is working within or with a human being, then we need to think also of user modeling, the user model acquisition, the application of that information from the user model to support its learning, to support the agent's learning, to support the inferences it might do or the decisions it might take. And if we go back to our previous example of Amazon, we can see how such recommendations happen through the interface interaction. Okay, so there are the user's purchases statements about ownership and ratings. This data is summarized, as well as a set of products positively valued by the user. So there's the construction of the user model over there. This leads to item-to-item collaborative filtering with a list of recommended items and explanations. So you can see how there is this behavior that's adapted on the process of the user model. And then through some learning, we reach the recommendation. Now, if we focus on the idea of assistance in the broad sense, we see that such systems would need to be aware of and able to adapt to the particular needs of specific users. Now, after all, individual humans are different. More to the point, even a single person's habits and desires change over time. As such, creating a true personal assistant will require access to the user's personal data and individual behavior, and will result in moving beyond fairly static personal computers to provide an adaptive and personalized information environment with information that is constantly being updated in relation to to the needs, to the ever-changing needs of the user himself or herself. Now, there are trade-offs, okay, in shifting the balance between user and proactivity. Users, in general, know what tasks they want to accomplish and have the requisite information, while computers can only infer what users want and must typically work with limited information. On the other hand, users have limited attention, memory, and cognitive capabilities, whilst computers have large storage, multitasking, and computational capabilities. So there's the trade-off over there. We've got a user that presumably knows what he or she wants, okay, but they have limitations, whilst the computer will have limited access to human information, but can really predict and carry out the tasks, the goals that human has more efficiently, or certain tasks more efficiently. Now, when designing an adaptive interface, we must find an appropriate balance for these, these trade-offs. However, finding that balance is difficult because we lack an understanding and appreciation of the full extent of the interface design space. Let's consider this, okay? There is, here on the slide, there is an example. It's actually a simple example, but it's an example of an alarm clock. An alarm clock which becomes intelligent depending on its evolution. Right, there's the alarm clock as we're used to. So it's a do-it-yourself alarm. Set your own alarm for the next day. There's an alarm clock with that is slightly a bit more intelligent. It actually tells you to pay attention. Did you check your alarm settings? Did you set your alarm for tomorrow? All these. So this is not impossible, something that is doable. It's not that doesn't involve lots of intelligence, okay? The cost of failure is low, the interface is really non-intrusive, and it needs little information to work with, okay? So that can be doable. There's a step forward where the alarm clock would tell you what to pay attention to. So let's say the alarm clock has information to the weather report, okay, for the next day. And not just the weather report, but also to the traffic updates. So the alarm clock will know, for example, that there will be rain tomorrow, and that there will be roads that are closed that might cause some congestion, and therefore it tells the user that there will be rain tomorrow. Would you like to check your alarm settings? Okay, it's a bit harder, one, because we've got more we need more information here, okay? We need more access to information, we need access to reliable information, because it's also a matter of trust here. And the cost of failure can be moderate. The interface itself can be non-intrusive, you just have a pop-up, a notification for you to pay attention to, but definitely needs more information. And then we've got an alarm clock that makes suggestions. You might want to change your alarm settings because it looks like rain. And when it rains, it takes you not 20 minutes longer, but 2 hours longer. So you might want to change your alarm settings for that. So it's not just asking you to pay attention, but it's also making meaningful and reasonable suggestions based on some sort of rationality. Do you realize where the agent is coming in, where the agent's role is becoming more pronounced now? And this is where it gets much harder. The cost of the failure is higher. Why? Because the agent has become a little bit more complex than before. The interface is certainly more intrusive. Why? Because it's not just a pop-up on the notification. It can go beyond that. And it needs much more personal information, such as where the user normally goes to, which direction the user takes. So it's based on past history. Again, this is why it gets more intrusive here. Okay, because it has to have a more accurate user model of users' past actions, users' behavior, users' preferences and needs. And then you've got the very intelligent alarm clock that makes decisions for you. You might get an explanation if you're lucky, but with explainable AI, this sort of like is coming along. So your alarm clock sets the alarm by itself, so you really don't do anything, because your alarm clock has access to your Google Calendar, to Google Maps with traffic updates, to the weather report, to the email, because there might be, meetings within email, or discussions over email. So, and this is extremely hard because you need so much, you need so much concerted effort here. You need everything to work in sync. You need to verify all the sources. And basically this is quite intrusive because it's intruding on a person's life, because it's taking decision on behalf of the user, because there's less control from the user and there's more autonomy for the agent. And of course, here we definitely need a lot of mostly personal information. There's also something else that's also a bit difficult to achieve, and these are twofold when it comes to privacy. So how much should an agent have access to personal information, and what is the agent really going to do with that? Where does the information go? How is the information stored? Who has access to that particular information? And what is this information, really used for? So there's that. There's also the fact that there's, as I said, more autonomy by the agent, leaving the human with less control, maybe. And also a matter of trust. So would a human really trust an AI, an agent, to take decisions about when the human should wake up, not to be late for a meeting? I mean, sometimes if we take into consideration certain traffic congestion rules, the alarm clock might be set for something like 5 o'clock in the morning, to make so that the agent makes sure that you get to the meeting in time. But, we are humans. We say, okay, I'll just make a phone call and say I'm late, or do the meeting from the car. Okay. How rational do we want the decisions to be, and how will they impact the quality of life of people? So we have to be very careful about, the level of autonomy and rationality that an agent acts with and in. So in summary, we might discuss the functions of user adaptivity in terms of the following: supporting system use and supporting information acquisition. And in supporting system user adaptivity, we may take over parts of routine tasks or adapt the interface for better use, but it can also help the user to exploit the full system use, and it is, as we mentioned before, a mediator to facilitate interaction. Okay, so this is how we support system use. So taking over parts of routine tasks, adopting the interface, helping with system use, mediating interaction with the real world, and controlling a dialogue. When using user adaptivity to support information acquisition, then the intelligent agent will help users navigate through and find the right information at the right time. We recommend the right products based on the current preferences, tailor and present information in the most meaningful and useful way for the user. And it will also provide different ways of supporting collaboration and supporting learning in the way which is more adequate for the user. Okay, so we have supporting system use, supporting information acquisition. Now, when data is collected from the user, models need to be used to build user adaptivity. User models are most often ontologically driven structures. We know that by now, that show a broader picture of the user's possible actions or needs described by feature sets. Now, depending on the context, in order to learn about user preferences, we might be using deep learning algorithms or logistic regression classifiers. Now, the key difference between user adaptive systems and other interactive systems is the inclusion of some method for acquiring and exploiting a user model. What is needed are some implementation of the adaptation algorithm, not necessarily embedded in any interactive system, and a database of behavioral data from a number of users who have used a relevant non-adaptive system. The researcher can then apply the modeling method to the data in order to determine how well the system would adapt to the users in question. There is, of course, ample research ground for the future of adaptive systems. There is a growing need for user adaptivity, as you know, so there is much work to be done to cover, for example, the diversity of users and contexts of use, as well as the scope of the information, including number and complexity of interactive systems, etc., etc. Finally, there is much research in the area of HCI that deals with the increasing feasibility of the success of the adaptation in terms of how the information is gathered from the users and how learning about the users happens. Okay, this is where AI techniques can be experimented with. So advances in techniques for learning, for inference, for decision, and attention to empirical methods. Okay, so that is all that I had to discuss with you today. There are a number of papers that you should refer to, should have a look at when looking at the topic. I suggest that you read through them. You will have a task that you will need to complete by next week, and you will be receiving an email with the instructions and information about how to carry your task for next week. Thank you for your attention.